I'm going to start with the two-dimensional and three-dimensional symmetry from section 14.8. Some people have no problem with this because they visualize things really well. Some of us have a little more difficulty with it because I, for one, sometimes have some difficulty, especially with three-dimensional ones, recognizing things. This section hopefully will help a little bit. Now, you basically have to remember the four types of symmetry. That for two-dimensional, you have line symmetry and rotational symmetry, and then that for three-dimensional symmetry, on the other page, you have plane and axis. The concepts are actually still the same. It's just with three-dimensional it looks different because you're dealing with a plane instead of just a line and an axis instead of a point. So it's sort of like you're going up a level when you do three-dimensional, but the concept's still the same. So the basic idea with line symmetry is a reflection. And sometimes you have multiple ones, like you can see with this, and I think this is like one of the examples in the textbook. You can have three lines here, three lines of symmetry that on this kind of a figure. And some figures you can have more. If you have a square, you've got at least four. You actually have more than that because of the different ways that you can split it, either diagonally or vertically and horizontally. You have four, or you have more. Play with that one. But here you have three different lines of symmetry in this one. In rotational symmetry, you need a point where it rotates around. Okay? And so in this case, in most of them, you're looking for the point in the middle, at which point place it could like rotate around as if it was spinning. And rotational symmetry is this idea that it maps onto itself as it turns around. So it becomes the same thing. In this one, if it were to come down like this and turn that way, and that point goes to here and here and here, you now have the exact same figure. It hasn't changed. It's the exact same figure. That's called mapping on itself. It means it looks exactly the same. And you can do it once, and you can do it twice, and you can do it three times. So the order of symmetry is how many rotations it makes. So it makes 1, 2, and 3 by the time it gets back to it. So in this case, there's an order of symmetry of 3. Based on that, you can figure out the magnitude of symmetry. All that is when you do the first rotation, what is that in terms of degree? And you haven't had as much experience with all of the degrees with things you'll do, like when you get to integrated 3 and then pre-calculus, you'll be doing the unit circle where you'll know everything from 0 to 360 quite well. One entire circle from beginning to end is 360 degrees. So if you are doing 3 stops, all you really have to do is divide that by 3 to get what this degree is to here. So that's 120. This is a 120 degree turn. So from here to here, if you think about it, this angle that you make by doing that is a 120 degree angle. So in this case, the magnitude of symmetry is 120 degrees. You do another 120 degrees to get to the second of the rotations. And the final 120 degrees gets you to the last rotation. You get it back mapped onto the beginning, and it makes a total of 360. So if you had something like a square, it would rotate once, twice, 3, 4 times, and you get back to the beginning. So that would be 360 divided by 4. You basically make a 90-degree turn each time. Yes?
How many times do you rotate a circle?
That's a very interesting one, and that's why we have a sphere on the next one, because it is you can either say there really aren't any because you're not having a stopping point, it just continues, or you could say there's infinitely many of them, which is probably more correct, because if you think about it, you could turn it a slight half degree, another half degree, another half degree, or a quarter degree, a quarter degree, a quarter degree. You'd have to say there's an infinitely many number of rotations you can make with a circle. I will not give you a circle. We will stick to figures that are more reasonable for that. That's a good thinking question for that. On the bottom, there's some example ones. This one's not a square, but a rectangle. So if you think about it, it can still have lines of rotation or lines of symmetry. You can have a couple of lines going that way. You can't have diagonal lines like you would with a square because it won't be the same thing. But you have at least 2 here, or at least that's all you have on that one. And then if you did this and you rotated it, you could rotate it once, rotate it, start rotating, and you'd have to go halfway around. So think visually about what would happen if you took that, no, 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 aha, halfway around, and it's back to the same thing. So this one only has an order of symmetry of 2. Okay. When you look at this one here, it looks like I could cut a line right through here, and it would reflect on each other. That would work. So it looks like there is one rotation that it can, not rotation, one line of symmetry that it has. I can't see any other way to make it exactly the same if I were to cut it in parts. But for rotating it, there is no way. There's no way you can get it until you get all the way back around. So there is no in-between spot, which means there is no, this one has line symmetry, but not rotational symmetry. So it really is looking at it, thinking about what happens, even moving it if you need to. And since this one is a regular pentagon, you do have some places where if you think about it, you can just cut down here and recognize you can also do it sideways here, and you can do it here. Every one of the vertices allows you or gives you a place where you can cut it in half and have it reflect. So this one, you can see, would have 5 of them, 5 lines of symmetry. And then if you rotated it, it would be almost the same thing. If I rotate it once, twice, 3, it looks like it would rotate 5 times. And that's where you want to think about what happens as you move it around. Okay? So this could go here, and then here, and then here, and then here. It's going to be the same thing as you rotate it each time. I tried to be very careful to make sure this was a regular pentagon, because if it wasn't, if it was more shaped like, let's see, I guess this one would be 6 sides now, 3, 4, 5, more house-like, then on this one you'd have a line of symmetry, and when you rotate it, there is no place where it's the exact same. The only way that this one works is if all the sides are the same and all the angles are the same, which you remember is how you determine a regular figure, in this case a regular pentagon. So that has some rotation, this one does not. Let's take a look at the next page. Now we're talking 3-dimensional symmetry, and this is where you have to remember that you have plane symmetry and axis symmetry, and the words matter. So when you're talking about 3-dimensional, don't call it line or rotational. Plane symmetry, as opposed to having a line go through it, think of it as a piece of paper that you slide in the middle of it, or a board or something that cuts through it. So a plane is a flat area like a desk. And you could do that here by having a flat one go right through the middle. In fact, similar to what you said about a circle before, Jay, here with a sphere, you could have a plane go this way or this way or this way. There are infinitely numbers of planes that you could have go through it. So here you simply say, yes, it has plane symmetry. You can't really give a number for this because it's an infinite number. And actually, I won't be asking for a number. I'll just be asking, does it have plane symmetry or does it not have plane symmetry? Yes?
I was going to say you could say like it's infinite.
If you'll notice in the textbook, they only ask yes or no. They don't ask how many.
Yeah.
They do for line symmetry, but they don't ask that for the 3-dimensional one. So that I'm sort of following that too for it. Especially if something like this one, it doesn't make sense. You could do that on some of the others, but it's not really done on this one. For a line of symmetry, well, that's similar here on this one. It was a point that it rotated around. Now, if you drew a line straight through it and rotated around it, then it would have symmetry. Like take this for instance. If I had, one of the few people you ever meet who uses a straw for his coffee. If this was a line right through the middle of it and then I rotated it, because of this top, it would not have symmetry. But, let's see if I can do this without having any coffee go on. Now, if I go down, if I have this line, I can't really do it showing up there, but if this was a line going right through the middle, this one has axis symmetry because this line, this axis here, now works where it just rotates around, and multiple times because it's a cylinder. If it's something different, well, actually, look at the ones down here. This one's a cylinder, so it's just like my coffee cup. So this one here, if you had a line right down through the middle of it, because it's a rectangular prism, you could really only rotate it once, twice, 3, 4 times. So this one could have a number with it if you want to say it. But what you can say is that yes, this has axis symmetry. If you cut right through the middle here, or right through the middle here, or down sideways, you have a number of ways where you can say it has plane symmetry. So this one does indeed have both, plane and axis symmetry. So does this one, because you can slice it here, or you can slice it right through the middle with a plane, and you could have a line go through just like, let's see if I can do it this way. There, now that sort of looks like they're straight, but I'm not getting any words from my drawing. But if you had something like a straw or something going through it like that, it's going to rotate around that, so it has axis symmetry as well. This one, though, I don't think there's any way that you can have an axis go through here to have it rotate around, although, let's think about it. If you had it come down through this middle, come down to here and come out through there, so I guess I can't draw it that. And you rotate it around, no, because if you rotate it halfway around, this is going to be on the other side now. So this one doesn't have axis symmetry. It doesn't look like we can set it up for axis symmetry at all. But plane symmetry, you can put a plane right through here, and that's going to have these two halves map each other. So this one has plane symmetry, but it doesn't have axis symmetry. And that's why you want to think about and even draw through something if you need to. So your job in this section is to remember the differences between the two-dimensional symmetry, two-dimensional figures and three-dimensional figures in terms of whether you're using a line or a point to rotate around, or a plane, or a line, or a line of axis. Okay. And that, I think, is actually a pretty good summary for the symmetry section.